So in this video, we're going to talk about that first step of the algorithmic analysis process, which is code modeling. Taking code and trying to come up with a function that describes its runtime. One thing that's important to mention, and I kind of alluded to this in the last video, is that today we're going to be talking about runtime. But for code modeling, you can really abstract this to this idea of any cost model. The cost model is really just an abstract idea. It's a mindset you might use in your analysis to express which resource we care about when we're trying to measure the growth rate with respect to the input size. So we're going to be talking about runtime. How long does it take the code to run? But other cost models exist and are very useful. For example, thinking about how much storage space, how much RAM your computer takes up, or how much energy it uses. Really interestingly, when you think about when people compare algorithms for databases, things that kind of back most of the internet or a lot of data science applications, when you compare different algorithms that run inside these databases, the cost model they use is thinking about how many times do you actually have to go to the hard drive to read data. Because one thing about computers is the hard drive is usually one of the slowest components. And so really, because there's a lot of stuff going on there, when they analyze their algorithms, they might just look at how many times you have to actually go to the hard drive and read data, and that's how they model their cost, not in terms of time or how much memory it takes up. So lots of things you could use for a cost model. And so the process of code modeling is coming up with a mathematical representation of that cost model. And so for us, when we're thinking about runtime, the code modeling tool we're going to use is, in some sense, the number of operations that a piece of code will need in order to run based off its input size. So it's going to be a function that describes how many operations need to happen in order to finish it that relates to the size of its input. And so another way of phrasing this is converting code to a function for its runtime. But again, remember, this could be generic to any cost model that you want. So what is an operation? We're going to be a little hand-wavy here for this video. I know I keep saying we're going to be hand-wavy and we'll come back to it, but it is something that's important to start thinking about now. An operation is something simple that the computer can do. Now, one of the things we're going to make is a simplifying assumption that every operation, or every basic operation, will take the same amount of time to run. Now, that is not a reasonable assumption. It's, in fact, very not true, but it's actually going to work out for us from what we'll see in the later videos. So what do we call a basic operations? Things like arithmetic or comparison. So plus, minus, divide, comparing equals or less than. We call those basic operations. Things like assignment or just returning a value or accessing a variable or an index in an array. We call those our basic operations, and we're going to assume each one takes the same amount of time. We'll call that amount of time one step or one operation. Then you might be familiar if sometimes in 143 they discuss it in this detail. If you have a function call, to call that function, you incur the number of steps in its body. And as a point to remember, whenever you construct a new object, that's also a function call. It calls its constructor. Conditionals, it's going to be the time that it takes to test the if statement, so whatever test you have in there, so how many steps that takes, plus the amount of time or the number of steps in the branch that's followed. And we're going to actually hold off on conditionals or complex conditionals for a bit. How do you reason about like an if and an else? We'll talk about that later. And then for loops, well, that's the number of iterations of a loop times the total runtime of its condition when you have to evaluate should you enter the loop, plus the runtime of its body. So that's the total number of steps for both. And again, remember, this is not a valid assumption that all these basic operations take the same time, but it's still a useful assumption for our discussion right now, and we'll see why that assumption is okay to make. So that's all been very abstract. Let's do a concrete example. So here I have a method that I want to analyze. I want to model its cost in terms of the number of steps, the number of operations. And so I'm just going to go down the line and just count up the number of basic operations. So that's a variable assignment. We said that was one basic operation plus one. There's another variable assignment, another plus one. Now we get to this while loop. Well, the condition of the while loop, I is less than n, that's going to be one step. And then in its body, the first thing it does is sum equals sum plus I times 3. And that's a variable assignment, a plus operation, and a times operation. So I might call that plus 3. And then for I equals I plus 1, that's an assignment plus a plus, that's 2 steps. And then a return is 1 step. Now, it's not as simple as just adding up all these numbers and being done, because you might notice that, well, since it's looping, it needs to actually, we need to count how many times it's going to loop and add up its steps for each body, or for each iteration of that loop. And so it's a little bit confusing, but we wrote this out like a while loop, but it starts at 0, goes less than n, and then increases I every time. So we know that these 6 steps in total, notice I just took these 3 different step counts for everything about the loop and add them up to a total of plus 6. That's going to run n times. So this loop on its own is going to take something like 6n steps to run. And then we could just add up the runtime of the whole body by saying 6n plus 1 plus 1 plus 1, which is 6n plus 3. This is a function that describes the number of steps the computer would need to execute in order to run this code. Now remember, we're using the number of steps here as a proxy. We're using it as a proxy for the runtime because it's hard for us to actually measure, oh, an assignment takes 0.1 microseconds or something like that. We're using this as a stand-in to say, okay, this should be good enough to give us a good estimate of approximately how long it'll take to run. It's not an exact timing mechanism. So we can come up with this function and say, hey, this whole function will take something like 6n plus 3 steps. Now recall, we made this simplifying assumption here that all operations take the same amount of time, that an assignment is the same as the actual while loop condition check. Now, this doesn't seem like a very likely assumption to be true, and in fact, I even said it's not a true assumption. Is it really the case that an assignment is just as expensive as comparing two numbers or arithmetic? How do we know that? And that's actually part of the reason why we make that simplifying assumption, is because it's actually really dependent on a lot of factors. The hardware could be specialized for one particular operation, and so on one computer, one operation might be faster than the other. So we try to make this simplifying assumption here. Another thing that's a bit hand-wavy here is when you look at this line that says sum equals sum plus I times 3, we say that's 3 steps, but is that actually 3 steps? Maybe there's actually more steps that happen behind the scenes, like the computer has to create the new variable or find where that variable is. Maybe it's actually more steps than just 3. And so we're going to hold on to this for a second and talk about why it's okay to make the simplifying assumption in the next video. But for now, I want us to do one more example of trying to do this code modeling process. So here's a more complex example with nested while loops. And notice here, we're using while loops instead of for loops to try to make it a little bit more clear kind of where the work is happening for the looping. But you would probably actually write this code as for loops in real life. Let's do our counting strategy. Starting at the top, int sum equals 0, I'm going to make that a plus 1. Then int I equals 0, plus 1. The while loop check, I is less than n, that's one comparison, 1 step. Making a variable assignment, 1 step. Making the next while loop, I'm going to count up, for that condition, j is less than n, that's plus 1 step. And then I'm going to go analyze the body of this loop. So this if statement, it has a j mod 2 and equals 0, that's 2 basic operations. And it doesn't actually matter if we do enter that if statement or not. I just have a comment in there, so there's nothing to do in its body. This line of code, sum equals sum plus I times 3 plus j, that's an assignment, and a plus, and a times, and another plus. That's a total of 4 steps. And then the last line there has plus 2. The line of I equals I plus 1 is plus 2, and returning sum is a plus 1. So many counting steps here, and we're not even done yet because we haven't handled what happens when they loop. Let's start with that inner loop, the inner while loop, while j is less than n. In total, this while loop has 9 operations for each iteration of its loop. And using our same logic as the last slide, we know it's going to run n times. So in total, that while loop is going to be something like 9n steps. Well, now that we know the runtime of the while loop, the inner while loop, let's try to figure out the runtime of the whole body of the loop so we can figure out the runtime of the whole method. Well, in total, the outer while loop takes 1, 2, then 9n steps, and then plus 2 at the end. that's a total of 9n plus 4 steps in total to execute that whole while loop for one iteration. And how many times does that while loop run? Well, it's going to run another n times. And then, oh my goodness, this is getting so complex right now. Then, once we have figured out the runtime of the whole while loop, we add on all the extra bits, the +1s at the beginning and the +1 at the end, for a total runtime of 9n plus 4. All of that times n, plus 3 overall, to measure our steps. And you could see already how tedious this can get for more complex pieces of code. And again, how it's a little tricky when you say like, oh, that line of code is 4 operations, while this one's +2. And so in our next video, when we talk about asymptotic analysis, we'll see how a lot of these tiny details will just end up disappearing.